Good morning. This class is on digital to analog conversion. Digital to analog conversion involves translation of digital information into equivalent analog information. As an example, in a computer, the arithmetic logic unit performs operations with binary numbers and it will be producing result in the binary form. Since we cannot easily understand the binary form, we have to convert this into analog form so that we can store it in the pen drive, or we can see that in the monitor, or we can take a printout. So it is necessary to have digital to analog converters. There are two types of digital to analog converters: resistive divider network and binary ladder network. In this class, you will see the function of the resistor divider network. Now, converting a digital signal into an equivalent analog signal is to change the n digital voltage levels into one equivalent analog voltage. So, we have to design a resistive network that will change each digital level into an equivalent binary weighted voltage. Now, what is binary weighted voltage, or what is binary equivalent weight? Consider the truth table for the 3-bit binary signal. There are 8 possible digital signals. The smallest number is 000, which corresponds to 0 volt, and the largest number is 111, which corresponds to plus 7 volt. Between 000 and 111, there are 7 discrete levels. The weights of the 3-bit number is given in the top of the table. The lowest significant bit weight is 2 power 0. Then the weight of the next lowest significant bit is 2 power 1, and the weight of most significant bit is 2 power 2. Now, we have to construct a resistive divider which has 3 inputs, digital inputs, 2 power 0, 2 power 1, 2 power 2, and which will be producing one analog output. So, in this table, it is shown that 2 power 0 bit has a weight 1 by 7, 2 power 1 has a weight 2 by 7, and 2 power 2 has a weight 4 by 7. If you add all these bits, the weight will be 7 by 7, which is equal to 1. Now we have to design a resistive divider in such a way that the 1 in the 2 power 0 position will cause plus 7 into 1 by 7 is equal to plus 1 volt at the output. Here we assume that 1 state is plus 7 volt and 0 state is 0 volt. A 1 in the 2 power 1 bit position will cause plus 7 into 2 by 7 is equal to plus 2 volt at the output. A 1 in the 2 power 2 bit position will cause plus 7 into 4 by 7 is equal to plus 4 volt at the output. In general, the binary equivalent weight assigned to the lowest significant bit is 1 by 2 power n minus 1, where n is the number of bits. The sum of the weights must equal 1. So, 1 by 7 plus 2 by 7 plus 4 by 7 is equal to 1. The binary equivalent weight of any bit in general can be written as weight of that bit divided by 2 power n minus 1. A resistive divider that has 3 digital inputs and 1 analog output is shown in the figure. So in order to have a resistive divider, we must know the function of the resistive divider. The resistive divider has two functions. First, it has to change the digital input into an equivalent analog output voltage. Then the second thing is, all these voltages must be summed together. The 2 power 0 bit must be changed to plus 1 volt. 2 power 1 bit must be changed to plus 2 volt. And 2 power 2 bit must be changed to plus 4 volt. These three voltages representing the digital bits must be summed together to form the analog output voltage. This circuit shown in the figure does this function. Resistors R0, R1 and R2 form the divider network. Resistance RL represents the load to which the divider is connected and is considered to be large enough that it does not load the divider network. So this is the circuit for resistive divider network. Now we have to see how it gives equivalent analog output voltage and the summing operation is performed. For this, consider the input 0, 0, 1. So, this input is 2 power 0, which will be given the voltage plus 7 volt, and 2 power 1 is given the voltage 0 volt, so it is grounded. 2 power 2 is also grounded, so that the input is 0, 0, 1. The analog output voltage is taken here. Now, the resistance values are R0, R1 is equal to R0 by 2 and R2 is equal to R0 by 4. Since 2 power 1 terminal and 2 power 2 terminal are grounded, it's like having R1, R2 and RL parallel to each other. So the circuit resembles this diagram. R0 by 4, RL and R0 by 2 are parallel to each other. So using the law for parallel resistors, we can write 1 by R parallel is equal to 1 by R0 by 4 plus 1 by RL plus 1 by R0 by 2, which can be rewritten as 4 by R0 plus 2 by R0 plus 1 by RL. So this 1 by R parallel is equal to 6 RL by R0 into RL, or it is simply 6 by R0, or we can write R parallel is equal to R0 by 6. Using this, the circuit is redrawn like this. This R0 by 6 is nothing but parallel combination of R0 by 4, RL and R0 by 2. Now this is a simple voltage divider circuit. So you can use Kirchhoff's voltage law to find the output voltage VA, which is equal to the source voltage 7 volt into the voltage across which the output voltage is found, that is R0 by 6 divided by the total resistance R0 plus R0 by 6. So it is equal to 1, or we can say that VA is equal to plus 1 volt. Similarly, the analog voltages for 0, 1, 0 input can be found to be equal to 2 volt and 1, 0, 0 input can be found to be equal to 4 volt by using Kirchhoff's voltage law. Instead of using Kirchhoff's law, we can also use Millman's theorem to find the analog output voltage. According to Millman's theorem, the voltage appearing at any node in a resistive network is equal to the summation of the currents entering the node divided by the summation of the conductances connected to the node. The conductance is nothing but 1 by R. So in equation form we can write the output voltage V is equal to V1 by R1 plus V2 by R2 plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. If you have more than 3 resistors, instead of using 3-bit resistive ladder, if we use n-bit resistive ladder, then you have to take the sum of all the currents in the numerator, and in the denominator you have to take the sum of all the conductances. So in general you can write V is equal to V1 by R1 plus V2 by R2 plus V3 by R3 plus dot 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 divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus dot dot dot. I have rewritten the equation here. Suppose if the digital input is 0, 0, 1, then using Millman's theorem, we can rewrite the equation as VA is equal to V1 is nothing but V0, R1 is nothing but R0, and similarly V2 is nothing but V1, R2 is R0 by 2, V3 is V2 and R3 is R0 by 4. So we can write VA is equal to V0 by R0 plus V1 by R0 by 2 plus V2 by R0 by 4 divided by 1 by R0 plus 1 by R0 by 2 plus 1 by R0 by 4. Now V1, V2 are 0. So you have only V0 by R0. V0 is 7. So you have 7 by R0 divided by 1 by R0 plus 2 by R0 plus 4 by R0, which is equal to 7 by 7, which is equal to plus 1 volt. So by using Millman's theorem, we obtain the analog output voltage for digital input 001 as plus 1 volt. For digital input 010, using Millman's theorem, we can write VA like this. Now only V1 is plus 7 volt, V0 and V2 are 0. So you can rewrite VA as 14 R0 divided by 7 by R0, which is equal to plus 2 volt. For digital input 100, we get VA is equal to this equation, and here only V3 is plus 7 volt, V0 and V1 are 0. So we can write VA as 28 divided by R0 divided by 7 by R0, which is equal to plus 4 volt. So using Millman's theorem, we have seen that for digital input 001, VA is plus 1 volt. For digital input 010, VA is plus 2 volt. For digital input 100, VA is plus 4 volt. To summarize, a resistive divider can be built to change a digital voltage into an analog voltage, and we have to follow these following criteria. There must be one input resistor for each digital bit. Beginning with the lowest significant bit, each following resistor value is 1/2 the size of the previous resistor. The full scale output voltage is equal to the positive voltage of the digital input signal. The lowest significant bit has a weight of 1 by 2 power n minus 1, where n is the number of input bits. The change in output voltage due to a change in the lowest significant bit is equal to 1 by 2 power n minus 1 into V, where V is the digital input voltage level. The output voltage VA can be found for any digital input signal by using the Millman's theorem. Now we have another formula for modified Millman's theorem, which is given as VA is equal to V0 into 2 power 0 plus V1 into 2 power 1 plus V2 into 2 power 2 and so on up to Vn minus 1 into 2 power n minus 1 divided by 2 power n minus 1. This formula can also be used to compute the analog output voltage for any digital input. Now, the drawbacks of resistive divider are each resistor in the network has a different value. Since precision resistors are to be used, there is added expense. Then the resistor used for the most significant bit carries larger current because the value is low than that used for the lowest significant bit. For example, in a 10-bit system, the current through the most significant bit resistor is approximately 500 times as large as the current through the lowest significant bit resistor. For these reasons, a second type of resistive network called a ladder has been developed. So, in this class, you have seen the construction of a resistive divider in order to have digital to analog conversion, then the drawbacks of resistive divider. Thank you.